Hello, pre-calculus students! This is Mr. Bean, and we're going to have another lesson. In pre-calc, we're still dealing with sine and cosine graphs, but we're also going to throw in tangent to this, and this thing called phase shift. We'll get into that in a second. Reminder of what sine divided by cosine is. What is sine divided by cosine? What is that? It's tangerine. Tangerine, sine over cosine. I love it. Okay, the first thing is to make sure you understand we are not going to use a calculator on this stuff today on almost everything in this lesson. There'll be some things on the application you need it for, but for the mastery check, be aware you're not using a calculator. You can do this stuff. It's not that bad. We won't need one. You can use it to check your answers, but that's about it. All right, let's recall some things. The first one is last lesson we learned about a cosine graph starts with a maximum, and then after one period it would be back at a maximum, or if you went one period to the left, you would have a maximum there. And then halfway to the period would be your minimum. And with the sine graph, we learned that the sine starts at the origin here. The sine would be there, and then after 1 pi, it would be, and let me draw it like this, it would be in the origin but going up. So after one period, it would be going up again. And then if we want one period backwards, again, it would be positive slope going up. And halfway between there would be going down. You'd have a negative slope. All right, so that's all from last lesson. So just the general shape of the graphs, where it starts, that's very important to make sure we have. Today we're going to be talking about horizontal shift of a trig graph, how we can shift things either left or move things right. So here's our formula. This magical number here, the h, that's the phase shift. That's what's new for today for our sine and cosine graphs. It's how far we're going to move left or right. Now to explain this, here's a couple quick examples you might write down. So this one, this graph is moving right pi over 2. Notice that the coefficient, the leading coefficient in front there of the x, the coefficient of x is a 1. And then you because we have the 3 here that's being multiplied to the whole thing. Now, I know that seems really confusing, but look at this one. So we would have to rewrite this so that it looked like 3 times x. Now, how do we do this? How do we divide this by 3? We're dividing that one by 3. And we need to divide this thing by 3. Well, I don't think of it as division by 3. I think of it as multiplying by a third. So if you think of it that way, I'm going to multiply this by 1/3, multiply this one by 1/3, and then that gives us x minus pi over 12. So in that case, this one would be right pi over 12. Now, if you have no idea what I just did, I'm going to do it again here later in the lesson. So that was just a little bit of a taste of how you figure out phase shift from the equations. So we'll come back to this if you don't have all of that yet, if you don't understand it yet. We'll get it here in a minute. All right, first off, we'll do the graphing. Let's jump right into this. The amplitude here, the a in front of cosine, is just the number 1, so that's easy. Amplitude. The period is going to be 2 pi over b, which in this case is a 1/2 from this. And then how far is it shifting? It is shifting left pi over 4. Okay, so that's what this comes. We do remember when it's on the inside with the x, it's the opposite. Well, we need to clean up this period. That's not going to help us. 2 pi over 1/2, that equals 4 pi. All right, so there's our period. So let's figure this out. Use a pencil and very lightly, not a pen, it needs to be a pencil, very lightly put little X marks where the graph would be if we were not using the phase shift. Okay, so I'm going to ignore the phase shift completely here before I actually graph the real thing. So let's pretend it doesn't shift, and the sine would normally, no, this is cosine. Normally would be, I'm going to put a little X here, so do a light X, and then 4 pi later I will have another maximum. Well, this goes off the grid to get to 4 pi. So we'd have to go all the way out to 4 pi. So that means halfway to a period would be a minimum. Halfway there, and then again, halfway the other direction would be a minimum. Now that's creating a period of 4 pi. So you have a minimum here, 4 pi later I have a minimum. And then that means halfway between, we've got our x-intercepts, the equilibrium point. Whoops, halfway. Let's go back. Halfway in between, right there at the negative pi. All right, so these x values are to help me, these little x values, I don't mean x's, these x's are to help me know what would happen before I used the phase shift. Now, let's apply the phase shift. So we're going to take all of these points and move them left pi over 4, which on this grid is 1 line. It's 1 unit here. And then down there. Okay, so now I have, and this would be off the grid just a little bit. So that has moved it left pi over 4, and you can now erase the little x's, and we can sketch the graph. So we don't need to have those x's there anymore. And now we sketch the graph. A little bit hard to sketch this one. I probably should have given an example with a larger amplitude. That was hard to sketch. But there's the idea. So let's try this with number 2. We're going to set up all of the things we need first, which is the amplitude. The amplitude is a 2. So up and down 2 from the equilibrium. The period is going to be, oh, we can't do this yet. Look at that. Well, we can do the period. We know it's going to be 2 pi over b, which is a 2, the coefficient of x, which is going to equal pi. All right, so that's easy enough. But we can't figure out the phase shift when it looks like this. We need to factor out, and that's why I left you some space on your notes, we need to take that 2 and factor it out. So if we divide by 2, we just get x. You divide this by 2, you get pi over 2. Now you can see that the phase shift is right pi over 2. Okay, now before we can graph this, I didn't write down the vertical shift, so we probably should have put down a vertical shift here so we remember that it's also down 1, so be careful about that, which means we have a new equilibrium point. So I would draw a dashed line right down the middle for our equilibrium point to help us out, and let's put some little tally marks here. So some little x's. Sine is right going through our origin, quote-unquote origin point. It's shifted down 1 because of that minus 1. And then out 1 pi will be there, out another pi, and then this direction pi, this direction pi. So now remember, sine is going up. So it doesn't go up down to here, because this is remember, this is sine like this. It's going up, it's going up, it's going up, which means halfway between it's coming down. You got to be really careful about that with sine. So let's do this. Let's put the down pin stroke, or the pencil stroke, here halfway in between the up strokes. And now this looks really confusing. How do we graph this? It's not that bad, because we know sine is going, negative sine, so it's not going up. It's going down here. So with the negative sign, it's going down, so halfway between is our amplitude. So we'll go here, and then halfway between there, up 2, halfway between here, down 2, halfway between here, up 2. What the graph would have looked like before we shift it right, pi over 2. All right, what's next? Now let's actually get the real real shifted graph, and take this point, shift it right pi over 2, dot, right pi over 2. So your intercepts, you can see here, all these little equilibrium points, those don't change. What changes is the max and mins. So here we're going to shift it right pi over 2, which is 2 of these lines, there, and then you can continue to do this on your graph, and once you have all of the peaks and valleys, on my screen it's blue, then you can go ahead and fill it in, the rest of the graph. And there's our graph. We've shifted it down 1. We've shifted it right pi over 4. We can get rid of all these other tally marks, these little x's, although really you don't have to. Those are just placeholders. You don't have to get rid of them if you don't want. The main part is having our graph all in one piece there. All right, now we are on to some of the more challenging things that kids have to deal with in this lesson, and that is coming up with an equation if all you have is the graph. When it's a little trickier when you have a phase shift. So notice what the maximum is. It's a 4 right here. And where are these valleys? It's the -2. So the first thing is to draw your equilibrium point right down the middle. So if we know then that this thing is shifting up 1. We're going to write down all the things we know that's going on with this. What else do we know? We have a period of, let's see here, I have minimum point here and a minimum point here where it repeats, so therefore it's repeating every pi. So the period is, what is it? Oh, I said pi. Well, that also means that pi is equal to 2 pi over b, because that's what a period is. So let's solve for b. Multiply both sides by b. You get that over. Divide by pi. You end up with a 2. So b is a 2. What else do we need? We need the amplitude. So let's get a. The a equals, from the middle, how far up are we going? 1, 2, 3. So a is equal to 3. Now, how do we know if it's positive or negative 3? It could be either one. We could have a positive 3 or a negative 3. So on these, what I'm telling you is we're going to use a positive leading coefficient. So I'm going to force you to use a positive only. We won't worry about negatives, because then you could have an infinite number of answers. It also says we're going to use the closest phase shift. So if it's a positive sign, what is the closest phase shift? We've got from here, this is the point that gives us a positive leading coefficient because the sign value is going up. If we went here, it would be going down. So the phase shift is that we shifted right. How far? We shifted it just 1 tally mark, which is right pi over 4. Okay, that's all we need to set this thing up. So now we write down our answer, which is going to be y equals 3 sine of, now be careful here, our b is a 2, then we open parentheses, x minus pi over 4. That shifts it right pi over 4. Close the parentheses again, because that's the closed parenthesis for sine, and then we say up 1, so we're going to say plus 1. Now, we do need to finish this. We distribute the 2, and that's our final answer. I know I didn't leave you a lot of room right there. So 3 sine of 2x minus, distributes here, you get pi over 2. It reduces. Close parentheses plus 1. All right, there is our answer for this one. So you just distribute the 2, and that is our equation of this line. Okay, here's a quick little clip from a science fiction show that I love, that they address a question I've always wondered about dealing with phases.
Well, because it undermines my authority, that's why.
Bryce.
Ah, Miss Reese.
I'm having a little trouble with scene 27. It says that I'm out of phase, which means that I can pass my hand through solid matter, or I can walk through walls.
Yeah, because you're out of phase. Exactly.
So, how come I don't fall through the floor?
We're going to have to get back to you on that one.
All right, you might not be a science junkie like I am, but that's always really bothered me in shows when people are out of phase in a different dimension or something. They don't fall through the floor, but they can walk through a wall. I don't get that. Okay, here we go. Tangent. Now we're going to learn what the tangent graph looks like. So first thing is write this down. Tangent of theta is equal to sine theta divided by cosine theta. Or in other words, it's the y value divided by the x value of all these coordinate points, which are really, really small because I didn't have enough room on the notes, so I made it small. So hopefully by now you're getting used to this unit circle. We take the y value divided by the x value at whatever angle we're looking at. So let's start off with the easy ones, like 0. When is tangent going to equal 0? It's when the top is a 0. So when is the y value 0? Here. So let's find the tangent of 0 degrees, or 0 radians. So that's going to be a 0. When else is the y value a 0? Way over here at pi, so it's also a 0 there. And then it comes back around in a full circle again, and then this is 0. So that one's where the tangent value is a 0. What about at the pi over 2 mark, the 90 degrees? The x is a 0. Well, if I have a 0 on bottom, that is undefined. So right here at pi over 2, we get an undefined situation. That represents a vertical asymptote. That's the big thing about this. When you have 0 on bottom, remember that? Vertical asymptotes. And where's the other part? Here. This is where x is a 0 way down here. So we get that this one is also undefined, which also represents a vertical asymptote. Okay, now on these, the pi over 4, if you look right here, it's the same thing. Square root of 2 divided by square root of 2, the y divided by the x, so that's just a 1, Over here, it's the same thing divided by each other, except that one of them is negative. So that one is -1. And then here we have 5 pi over 4. They're both negative, so this is a positive 1. And then 7 pi over 4, one of them's negative, so we're back to -1. Okay, let's take this. I'm going to do a quick little screen capture so you don't have to remember all of these things, and paste it here onto the page. That way we don't have to go back and forth looking at the other slide. All right, I'm going to leave this here, cover up a little bit of stuff as we're trying to sketch our very first graph. So first thing, let's identify when do we have an undefined graph, because that will tell us when we have zeros on bottom of that fraction sine over cosine. If you remember that, sine over cosine. So when we have undefined, that's because there's a vertical asymptote. So let's start off with that. So we have pi over 2 is undefined, so right here let's put a dashed line, and then again at 3 pi over 2. So how often is our tangent graph repeating? Whenever we have a vertical asymptote, I'm having a hard time graphing that. Whenever we have a vertical asymptote, it is repeating itself. So it has it pi over 2, 3 pi over 2. The period lasts every pi over b. So this is important to have down on your notes. It is different for the period of tangent. If you remember, for sine and cosine, it was 2 pi over b. For tangent, it is different. Okay, that's a big hint here. One of the first things that people will get wrong on some mastery checks or tests is recognizing the period of tangent. So it's pi over whatever that b value is. So in this case, b is a 1, and therefore the period of this graph would be pi over 1. So it's just a pi instead of 2 pi. All right, let's keep going here. Let's sketch some other asymptotes. Let's go to this way. So if I continue the pattern, it would if I get to pi over 2, then I skip out a whole extra pi to get to -3 pi over 2, and there is my graph of tangent for the vertical asymptotes. All right, next, let's plot some points. So I've got 0, 0, and I have pi over 4 and 1. And then let's keep going here. I have undefined, so that's my vertical asymptote. 3 pi over 4 and -1, pi 0, 5 pi over 4, 1, and then you continue the pattern. So what is going on with this graph? I'll show you here. Let me finish getting these dots. This is what the tangent graph does. So I start here, and I sketch towards the vertical asymptotes, and this way down towards the vertical asymptotes. It almost looks like a cubic graph. Very similar to a cubic, except that it has vertical asymptotes here. Cubic graphs don't have vertical asymptotes. So you can fill in the rest of this, and there's your tangent graph. All right, one other thing that we can grab from our equation, and that is that this value of a right there, that helps us get a coordinate point. That coordinate point will be from the middle here. If we move over halfway to the vertical asymptote, then that value is our y value. Let me say this again. Whatever this is here in front, we're used to thinking of it as amplitude. Halfway to the vertical asymptote, that is our value of a. Halfway to the vertical asymptote from the middle, that is our value of a. So that helps us sketch the graph a little bit more accurately. Okay, so if you don't have all that down, go ahead and get it copied down. Let's go on to our last example, number 4. So the first thing is, let's recognize what the period is, and in this case, it is going to occur every pi over b. In this case, that's 2, so that's how often the period is going to occur. And let's look at the phase shift. So if I take a 2 out of this, I'm dividing by 2 here. It becomes an x. Divide this by 2, and it just becomes pi over 2. So let me show you how to do that again. Divide by 2 and divide by 2. It's like I make a fraction. So now the 2's in front. This becomes x, and this becomes pi over 2. So that means it's shifting right. How far? It's shifting right pi over 2. All right, so now it used to be that a tangent would go through right here at the origin. Now it's going to be shifted right pi over 2. So now it's going to be there, and then it repeats every pi over 2. So then I jump out another pi over 2. Whoops, here's a pi over 2, another pi over 2, another pi over 2. And we can go backwards on our period. Pi over 2 left, pi over 2 left, and so forth. and that just continues the pattern. Halfway in between these periods then, right in the middle of this, is where we have our vertical asymptotes. You're going to have a whole bunch of vertical asymptotes here. I'm not going to draw every single one. I'll just draw a few of them. And keep going, keep going. Now, halfway to the vertical asymptote, do you remember our A? Our A here is a 1/2. So if A equals 1/2, what does that do for us? It tells us halfway to the vertical asymptote, we have a value of A, right about there. And then that would also be down -1/2 that direction. So about halfway, halfway, and then you can sketch, oh, that's difficult to sketch that accurately. You can sketch the graph of that. So we're just looking, the quickest way for your teacher to grade this is when they can see that you have the correct vertical asymptotes, you have the correct middle points here, right on the x-axis, and then to see that you have the value of A halfway between the point and the vertical asymptote. That's usually the easiest way for us to grade. And that pattern just continues and continues and continues. We won't draw this whole thing here, but you need to have at least several of these on your graphs. All right, you are done. You finished the lesson. Congratulations. This next part is not absolutely necessary, so you could technically stop watching the video. You're finished, but it's cool, okay? Listen, Doppler effect. Some of you have had some physics classes. You already know this, but I've got a funny little clip to show. So when an ambulance is coming at you and it's racing towards you really fast, you hear the sound waves traveling from the siren, and it gets over here and it hits your ear. Let's draw an ear. That's like Mr. Kelly's big ears. So you get to the eardrum, and these waves are traveling really fast, so it's a high-pitched sound. So you've got the ambulance, but what does it do right as it passes you? You know this. Some of you know it. As it passes you, it goes, it gets a lower pitch. Do you follow what I'm saying here? So here, let's get rid of all these. Oh, he lost his ear. Oh, I'm sorry. And so when you get this guy standing here, and then the ambulance rushes past, right at this moment, the pitch is lower. Why is that? Because the sound waves are further apart, because the ambulance is racing that direction, and so the sound waves, instead of getting pushed towards your ear, they're now having to fight the momentum of the ambulance to get back to your ear. That is something cool called the Doppler effect, depending on how the waves, if the waves are really tight like this, or if the waves are spread out. Depends on the pitch of the sound. So here's a clip from The Big Bang Theory. You might have seen this before. It's pretty funny stuff about the Doppler effect. Rock that mastery check, and I'll see you back in the next lesson.
I mean, look at Wolowitz. He's not English, but he's dressed like Peter Pan. Sheldon is neither sound nor light, but he's obviously the Doppler effect.
I'm not Peter Pan, I'm Robin Hood.
Really? Because I saw Peter Pan, and you're dressed exactly like Kathy Rigby. She was a little bigger than you, but it's basically the same look, man.
Hey, Sheldon, there's something I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate.
Terrific.
So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
Hi, Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. I hate what Sheldon's supposed to be.
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Nice.
Hi. Hello.
So what are you supposed to be?
Me? I'll give you a hint.
Choo-choo train?
Close.
The brain damage choo-choo train? I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Well, why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect.